I want to explain in simple way. Total number of edges in Wn is equals to number of edges in Cn minus 1, number of edges in Cn minus 1 plus degree of hub. Is it correct or not? Total number of edges in Cn minus 1 and degree of hub. In this example, total number of edges in Cn minus 1 means, suppose if it takes Cn minus 1, how many edges we have? N minus 1 edges. Right? Number of edges in Cn minus 1 means N minus 1. Plus, what is the degree of hub? Obviously, that hub is connected to remaining all other N minus vertices, right? Therefore, we can say it is N minus 1. The total is equals to 2 times of N minus 1. Total equal to 2 times of N minus 1. Is it clear, everyone? Very simple. Total number of edges in Wn is equals to number of edges in Cn minus 1 plus degree of hub. Number of edges in Cn minus 1 equal to N minus 1 and degree of hub is equals to N minus 1. So therefore, 2 times of N minus 1. Who is hub in this case? D is called hub. In this diagram, D is called hub. Here, E is called hub. Okay. I won't write that point also. In our previous examples, D is called hub. D is called hub. Okay. Similarly, E also called hub. E is called hub. Right? So this is one way of analyzing. Or else you can also analyze by using some degrees of vertices theorem. You can also analyze some degrees of vertices theorem. Clear? Some degrees of vertices theorem. If you want to analyze by using some degrees of vertices theorem, summation I runs from 1 to n, degree of all vertices must be equals to 2 times of number of edges. If you observe, each vertex having in W4, for example, in W4, each vertex degree is equals to 3, right? Similarly, if I take this W4, each vertex degree is equal to 3. Similarly, if I take W5, in W5, each vertex degree is equal to how much? Look at this one. Each vertex degree is equals to 1, 2, 3. Here, each vertex degree is equals to 3. Okay. Now, if I consider W6, in W6, each vertex degree is equals to W6 diagram is looking like this. W6 means we must have 6 vertices. Where initially we have cycle graph with 5 vertices. It is cycle graph with 5 vertices. Correct? The cycle graph with 5 vertices. Now W6 means we have to create one hub which is adjacent to remaining all other 8 vertices. Okay. This is called W6. This is called W6. Now, what is the degree of each vertex? Degree of each vertex is like 1, 2, 3. Here also 1, 2, 3. So for this one also 1, 2, 3. 1, 2, 3. Here also 1, 2, 3. So degree of every vertex is 3 except that hub. Okay. But if you see hub degree always is equals to n minus 1, right? Always is equals to n minus 1. Okay. Therefore, in W4, each vertex degree is equal to 3, where hub degree is n minus 1. That equals to 3 only. See here, that is 3. In W5, each vertex degree is equals to 3, but hub degree is equals to 4, which is n minus 1. Okay, we want to include that point also. Each vertex degree is equal to 3, and the degree of hub is equals to 4. Here, degree of hub is equals to 3. Here it is degree of hub is equals to 5. So what did you notice from these examples? In Wn, suppose if you consider wheel graph of order n, in Wn, each vertex degree is equals to 3 only. In Wn also, each vertex degree is equal to 3. But if you take degree of hub is equals to n minus 1. Is it clear? By using this, if I take degree of all vertices, it will be divided into two parts. Degree of every vertex and degree of hub. So degree of every vertex, how much? That is 3. Like that, how many vertices we are having? V minus 1. Therefore, degree of every vertex is 3. Like that, we are having V minus 1 vertices. And the hub is called one vertex, right? That vertex having degree V minus 1. How many such vertices? 1. This is equals to 2 times of number of edges, which is equals to, it is 4 times of V minus 1 is equals to 2 into number of edges. So 2 get cancelled 2 times. Therefore, number of edges is equals to 2 times of number of vertices minus 1. Okay, where vertices means here n. Okay, therefore, the final answer is number of edges equal to 2 times of n minus 1. So the different way we can analyze the formula in order to get number of edges in wheel graph. Okay, I explained 2 different approaches. Okay, in W4, each vertex degree equal 3 and degree of hub is equal to 3. Each vertex W5, each vertex degree equal to 3, degree of hub is equal to 4. In general, in Wn, each vertex degree is equal to 3 and degree of hub is equal to n minus 1. Therefore, whenever they are talking about sum of degrees of all vertices, this is for what purpose? It is for hub purpose. It is remaining vertices. Clear? There is only one hub which is having degrees V minus 1. Okay. The number of vertices is equals to n. Right? So that is the definition of wheel graph. Is it clear, everybody? Okay. Next. After completion of wheel graph, next we'll discuss a regular graph. Regular graph. Suppose in a simple graph, if every vertex degree is k, then it is called k regular graph. Okay. If degree of every vertex is k, then it is called k regular graph. Then it is called k regular graph. Let me take a quick example. Suppose here degree of every vertex is 2. Therefore, we can say it is 2 regular graph. Here degree of every vertex is also 2. Therefore, we can call it as a 2 regular graph. And I can take degree of every vertex is 3, which is 3 regular graph. Regular graph. Okay. In general, every cycle graph, which we covered earlier, every cycle graph is a 2 regular graph, because in cycle graph, degree of every vertex is always 2 only. Therefore, it is 2 regular graph. Okay. Every cycle graph is 2 regular graph. Every cycle graph is 2 regular graph. Right? 2 regular graph. And by using some degrees of vertices theorem, we can say summation I runs from 1 to n, degree of all vertices must be equals to 2 times of number of edges, correct? But this time each and every vertex having how much degree? Degree k. Therefore, k into number of vertices v is equals to 2 times of number of edges in k regular graph. It is also most important result. Most important result. Okay, you have to remember this result. In k regular graph, k into number of vertices equal to 2 into number of edges, because by using some degrees of vertices theorem. Okay. Next, here I want to introduce some important basic key points. That is, first one is small delta of g. Generally, small delta of g is called minimum degree of all vertices. All vertices. And capital delta of g is equals to maximum degree of all vertices. Maximum degree of all vertices. So these two notations are useful for discussing remaining definitions. For example, if you take 5 vertices graph, it will be A, B, C, D. A, B, C, D, E. Okay. So clearly degree of A is equals to 1. Degree of A equal to 2. Sorry for the mistake. And degree of B is equals to 2. Okay. And degree of C is equals to 2. And degree of D is equals to 3. 3. Degree of D is equal to 3. And degree of E is equals to 1. Here, among all these degrees, which is the minimum? Minimum is 1. That is denoted by small delta of g. Which is the maximum? Maximum is 3. That is denoted by capital delta of g. Is it clear? So minimum degree is equal to small delta of g, and maximum degree of g is equals to capital delta of g. Okay. Here, small delta of g is equals to 1 minimum degree, and the maximum degree capital delta of g is equals to 3. Right? Suppose if I want to find average degree of a vertex. Average degree of vertex formula is sum of degrees of all vertices, sum of degrees of all vertices by total number of vertices. Total number of vertices. So that is the meaning of average degree, right? So sum of degrees of all vertices means by using some degrees of vertices theorem, some degrees of all vertices must be 2 times of number of edges by using some degrees of vertices theorem. And total number of vertices we can say V like this. Total number of vertices. Therefore, average degree of a vertex is equals to 2 into E by V. 2 into E by V. In this example, In this example, if I compute this value, sum of degrees of all vertices, 2 times of number of edges. 2 times of number of edges. How many edges we have? 1, 2, 3, 4, 5 edges. So therefore 2 into 5 by number of vertices. 1, 2, 3, 4, 5. 5 vertices, which is equals to 2. That is average degree of all vertices. Okay. This average degree of all vertices value is 2. This value is equals to 2. Value equal to. Tell me, is this 2 greater than small delta of G? Is this 2 greater than small delta of G? Yes. Is this 2 less than capital delta of G? Yes. Therefore, I can say that small delta of G value always less than or equal to, remember this basic formula. Small delta of G always less than or equals to average degree of a vertex, which is less than or equals to capital delta of G. Okay. Tell me, what is small delta of G? Minimum degree. What is capital delta of G? Maximum degree. It is satisfying the condition minimum degree of vertex must be less than or equal to average degree of vertex less than or equals to maximum degree of vertex. Like in algorithm subject, best case time complexity less than or equal to average case time complexity less than or equal to worst case time complexity. Here, best means minimum, average, and then worst means maximum. Okay. If I can continue this one, this is equal to delta of G, small delta of G less than or equal to. But what is value? What is value? What is the value of average degree of vertex? So that we have already written here. That is 2 times of E by V. 2 times of E by number of vertices, which is nothing but 2 times of E by number of vertices, less than or equals to capital delta of G. Okay. So this formula is also most important formula in order to evaluate work product examples. Right? So please remember this formula. Okay. So what we covered so far, we started with complete graph and its properties. Afterwards, we defined cycle graph. By using cycle graph, we defined wheel graph. Right? After wheel graph, we have seen what is the minimum degree of vertex and what is the maximum degree of vertex. What is the relation among minimum, maximum, and average? Okay, this is the relation among those. Right? Next, we'll discuss bipartite graph. We have another 2 more definitions. Let me finish. Maybe length of the video is more than 1 hour. No problem, because if I keep all basics in single video, then only we'll get complete idea. Otherwise, I can create 10 minutes, 10 minutes videos. You will not get complete idea about all these concepts. That is in creating 1 hour length video. Okay, so please don't feel bored. Next one is bipartite graph. So I'll explain the definition of bipartite graph by using simple example. See, you'll get more clear idea after practicing workout example. I'm going to introduce minimum 25 workout examples. You please practice them. You'll get complete idea about all these formulas. Okay. Suppose assume that I have 4 vertices like A, B, C, D. There are 4 vertices. I'll take another example also simultaneously so that I can quickly explain the definition of bipartite graph. one more. ABC. Let me take one more example. Right. So look at this first graph. Look at this first graph. This graph contains exactly four vertices, and four edges. Four vertices and four edges. The second graph contains six vertices, and number of edges also six. Next one, three vertices and three edges. Next we have five vertices and then five edges are there. Okay. Of course, we'll take another example also, but let me explain this example first for bipartite graph. See, when we say graph is bipartite graph, we can say graph is bipartite graph if the number of vertices of that graph can be split into two sets. The number of vertices of a graph can be split into two sets. Okay, two sets. Suppose the given graph is g of v comma e. Isn't that given graph is g of v comma e is a given graph. Now we have to split this v into two sets. Say m and then n. We have to partition v into two sets m and n. Then every edge in G, every edge in G joins a vertex from M to the vertex in N. Repeating once again, we have to divide the given vertex set into two sets, name them as M and N. Then every edge of the graph must join a vertex in M to the vertex in N. Then that graph is called bipartite graph. Maybe you may get confused. Let me explain here. Total, we are having four vertices, right? These four vertices, I'm going to divide into two sets. Two sets. Okay. What are the sets? For example, I can say it is vertex A, another one is vertex C. Okay. Here I have vertex B and that is D. Clearly, we divide four vertices into two sets. We can call this set is M, this set is M, and this set is N. Two vertices set. Now, what are the edges are possible here? A to B edge is there. A to B edge is there. Therefore, we can create A to B edge. A to B. And also we have edge from A to D. A to D. Okay. We have edge from C to D. Therefore, we can draw C to D. And we have edge from C to B also, like this C to B. So the given graph is converted like this. Okay. The given graph is converted like this. Okay. In this case, what is M now? M indicates M contains two vertices. What are they? A, comma C. And N contains two vertices. What are they? B, comma D, like this. Okay, B, comma D. Therefore, the given vertex set V divided into two sets, name them as M and N. Then every edge in the given graph G is joining a vertex from the set M to the vertex in the set N. Okay, in the a vertex in the set N. That type of graph is called bipartite graph. But remember, we cannot join A and C. We cannot join A and C. It means no two vertices of same set can be connected. No two vertices of same set can be connected. Please understand. Okay. Now let me check this one. Check this one. We can divide this graph into two sets. Like I can name them as one set contain A, another one is C, another one is F. Okay. Another set contains remaining vertices B, D, and then E like this. Okay. E. Now suppose if I take edge A to B, I can draw edge from A to B like this. A to B. Next A to D also we have edge. We can draw A to D. Next C to E. I can draw edge from C to E. And C to B, draw edge from C to B. Okay. Next F to E, draw edge from F to E. Draw edge from F to D. That's all. So that given graph will be converted like this. That given graph will be converted like this. Okay. This part, whatever is there, M is equals to here. Set of all vertices. What are they? A, C, F. And what about N? N is equals to B, comma, D, comma, E like this. D, comma, E, D, comma, E. Is it clear? Now the definition of bipartite graph is looking like this. Definition of bipartite graph. Let G of V comma A be a graph divide the vertex set V into two disjoint vertex sets say M comma N. Okay, divide the vertex set V into two disjoint vertex sets say M comma N such that every edge of G joins a vertex of M to a vertex of N. Okay, and no two vertices of same set are connected. Means we cannot connect two vertices of M. We cannot connect two vertices of N. Okay, so that type of graph is called bipartite graph. That type of graph is called bipartite graph. Okay, let me take one example. You verify is it bipartite graph or not. Suppose I have five vertices like A, B, C, D, E. I'm joining from A to C. Is it bipartite graph? Yes, it is a bipartite graph only. It is bipartite graph only. Okay. A and C are connected, remaining are isolated vertices. I can say it is a bipartite graph. Okay. Next, another example. Suppose you can say it is example number. The first one is example number 1, which is example number 2. Now you can call it example number 3, which is also bipartite graph. Okay. Okay. Now I can take one more example. Like we have A, then B, C, D, E. Can I say it is a bipartite graph? Yes, it is also bipartite graph. Okay, which is example number 4. Okay, final example. Like A to C, and A to D, and B to C, B to D. Is it bipartite graph? Yes, it is also bipartite graph. Okay, but what is invalid bipartite graph now? Example 5. Okay. The invalid bipartite graph is we cannot join A and B. If I suppose join A and B, then it is not possible. Okay, it is not possible to have such type of edge in the bipartite graph. Okay, I hope it is very clear now, right? But if you observe example 1, example 2, example 3, example 4, example 5, in all these examples, all these are bipartite graph only. But if you observe example 1, every vertex of M, every vertex of M, what are the vertex of M? A and C. Every vertex of M is connected to every other vertex of N. Clearly, look at here. A is connected to B. A is also connected to D. C is connected to B. C is also connected to D. Means every vertex of capital M is connected to every other vertex of capital N. Right? Let me check example 2. What are the vertices in M? A, C, F. Is A is connected with every other vertex? Let me check. A is connected to B. A is connected to D. But A is not connected to E, right? A is not connected to E. Similarly, C connected to B, C connected to E, but C is not connected to D. F is connected to D, F is connected to E, but F is not connected to B. Okay. If you observe first example, every vertex in the set M is connected to every other vertex in the set N. Okay. So such type of bipartite graph is called complete bipartite graph. Okay. So what is the meaning of complete bipartite graph? Every vertex of the set M is connected with every other vertex of the set N. That is called complete bipartite graph. Okay. Let me take one more example to get clear area. First, let me write the definition of complete bipartite graph. Complete bipartite graph. Let G of E comma E be a graph. A graph. Now divide the vertex set M. Divide the vertex set V. Divide the vertex set V into two disjoint vertex sets M comma M and N. Divide the vertex set V into two disjoint vertex sets M and N. If every vertex of M is connected with every other vertex of N, every other vertex of N, then that graph is called complete bipartite graph. Complete bipartite graph. Note that no two vertices of same set are connected. That is basic key point, right? No two vertices of the same set are connected. Okay. So this is called complete bipartite graph. In general, complete bipartite graph. Suppose let number of suppose assume that number of edges, let number of vertices in M is equal to small m, number of vertices in capital N is equals to small n. Just assume that. Then the complete bipartite graph can be defined as, then the complete bipartite graph can be defined we can say it is can be denoted by km comma n, can be denoted by km comma n. Clear? So now let me take one example so that you'll get more clarity. Assume that I have 5 vertices A, B, C, D, E. I have 5 vertices. Okay. Okay. Now, if I call, suppose it is a vertex set M, and if I call it is vertex set N. Clear? It is vertex set M and it is vertex set N. Then every vertex of the set M is connected with every other vertex set of N. Clear? Okay. Observe. Suppose A connected to C, A connected to D, and A connected to E. Similarly, B connected to C, B connected to D, and B connected to E like this. This is called complete bipartite graph. Okay. This is called complete bipartite graph. It is generated by K2, 3. It means that one set contains 2 vertices, another set contains 3 vertices. Okay. Right. Let me take another example. Let me take ABC, and we are having D, E, F, D, F. Suppose A is connected to D, and A is connected to E, and A also connected to F. Next, B connected to D, B connected to E, B connected to F. C connected to D, C connected to E, and C connected to F. This is called complete bipartite graph with 3 vertices one side, and another side is also having 3 vertices. That is K33 graph. Okay. Is it clear or not? Right. Then one important point here to remember, in a complete bipartite graph, in a complete bipartite graph, in a complete bipartite graph, the total number of edges in complete bipartite graph KML must be equals to, just observe here how many edges are there in the first example. How many edges? Like 1, 2, 3. Okay, let me count properly. 1, 2, 3, 4, 5, 6. Total 6 edges are there. Means each vertex is associated with every other vertex of the graph or not? Yes. How many such vertices are there here? M vertices are there. M vertices are each and every vertex associated with n vertices. Therefore, M into N. Okay. Means A is associated with n vertices, B also associated with n vertices. Therefore, I can say A is having n possibilities and B is also having n possibilities, right? Like there are how many n possibilities means n like this, m times we can add, therefore m into n possibilities. Okay. How many vertices are there in A? M vertices, right? So A n times, B n times, like that we are having n. total m times m into n. The total number of edges are m into n. The second property is, if I ask the number of vertices of Kmn is equals to, how many number of vertices are there? The number of vertices are in Kmn. So clearly here two vertices, here three vertices, total five vertices. It means that m plus n vertices. Okay, m plus n vertices. Clear? So these are two important properties you have to remember in complete bipartite graph. Of course, in problems also we'll discuss again all these points. Okay. Right. Next. And the third important point, the most important point, maximum number of edges. Max number of edges in a bipartite graph. In a bipartite graph. I'm not talking about complete bipartite graph. Obviously, complete bipartite graph is that what number of edges are m into n. Number of edges are m into n. But here I'm talking about max number of edges in a bipartite graph. Okay. So max number of edges in bipartite graph. How will you get max number of edges in bipartite graph? Let me check simple example. Suppose the graph is having five vertices. Five vertices. Okay. Graph is having five vertices. Five vertices. Okay. Whenever graph is having five vertices, how many ways I can define bipartite graph means the bipartite graph may be looking like this. Here it is one vertex. The rest of the four vertices are here. I can define bipartite graph. Okay. So then let me make it as A, B, C, D, E. So A associated with B, A associated with C, A associated with D, and A associated with E like this, which is a bipartite graph. Of course, it is a complete bipartite graph also. Okay. If I have five vertices, I can also take the graph like this, A and B to the left side, and remaining C, D, E right side. Right side. Okay. So in that case, A is joining with C, A is joining with D, A also joining with E, and B joining with C, and B joining with D, and B joining with E like this. Okay. Clear? Of course, I can take three left side and two right side. Three left side and two right side. Okay. No need to draw that example. Okay. So if the graph contains five vertices, these are two ways I can draw complete bipartite graph, like K 1, 4 and K 2, 3. Remember, K23 same as K32. Okay. K23 same as K32. Therefore, no need to draw that one. Okay. In first one, how many number of edges are there? Number of edges is equal to how many? 1 into 4. That equal 4 edges only. But here number of edges, 2 into 3, 6 edges. 6 edges. Means if I take 5 vertices graph, and if I represent the form of complete bipartite graph, so one time I have 4 edges, one time I have 6 edges, right? Well, let me take another example. We'll get more clarity. Afterwards, we'll derive the formula. Suppose I have a graph with 6 vertices. Just imagine that I have a graph with 6 vertices. Then how many ways I can draw the complete graph now? Complete bipartite graph. I can take one vertex, right? One vertex one side and 5 vertex another side. Then how many edges we have? Number of edges 1 into 5, that equal to 5. Right? Or else I can take 2 vertices left side and 4 vertices right side. So number of edges equal 2 into 4, 8 edges. Or I can take 3 vertices one side and 3 vertices another side. Number of edges are 3 into 3. Because number of edges in complete bipartite graph is m into n, right? 3 into 3, 9. These are only possibilities we are having. Now, if you observe these two examples, we'll get max number of edges. Only if you divide the given vertex set into two equal parts. For example, see, If it is 6, it is divided into 2 equal sets. One set contains 3 vertices, another set also contains 3 vertices. 3 vertices. Is it clear or not? Then only we are having maximum number of edges. This is a case where we are getting maximum number of edges. Okay. Max number of edges. So what I'm trying to say finally, suppose if the graph contains n vertices, if graph contains n vertices, in order to get maximum number of edges in a bipartite graph, then maximum number of edges max number of edges bipartite graph generated by k n by 2 comma n by 2. So it will generate max number of edges. Okay. Then how many max number of edges are there in k n by 2? K n by 2 means that is equals to n square by 4. N square by 4. Okay. So therefore, max number of edges in a bipartite graph generated by kn by 2 by kn by 2 comma n by 2, which is equal to n square by 4. N by 2 and n by 2 means n square by 4. But here the problem is, for example, here 2 into 3 6, 2 into 3 6, here 3 into 3 9. Sometimes if I take n is equals to, suppose here n is equal to how much? N is equal to, first problem, n is equals to 5. N is equal to 5. Therefore, if I consider max number of edges, 5 square by, according to this formula, 5 square by 4. 5 square by 4 means that equal 25 by 4. 25 by 4 means 6 point something, correct? 6 point something. But actually, how many number of edges we had? 6. So therefore, this formula is not giving complete answer, right? This formula is not giving complete answer. Therefore, to get complete answer, it must take floor. Like this. Clear? Therefore, this is the most important formula. Maximum number of edges in a bipartite graph must be floor of n square by 4. Maximum number of edges in a bipartite graph where n is equal to total number of vertices. Where n is equal to total number of vertices. Is it clear? You have to watch this part 2 times, then only you can understand. So if I have a graph with 5 vertices, that graph I can write k1 comma 4 or k2 comma 3. Of course, k3 2 is same as k2 3. Okay, and k4 1 same as k1 4. That's the reason I didn't write. Suppose if I have 5 6 vertices, then 6 vertices I can write 1 comma 5 or 2 comma 4 or 3 comma 3. But which is generating more number of edges? That is k33 generating more number of edges. It means that I realize that if the graph contains n vertices, you have to distribute n by 2 vertices to one set and remaining n by 2 vertices to another set. Then only get more number of edges. Therefore, n by 2 into n by 2, that equal n square by 4. N square by 4. But in order to get exact result, you have to use floor. Therefore, maximum number of edges in a bipartite graph must be floor of n square by 4. Okay, where n is equals to total number of vertices. Where n is total number of vertices. Is it clear? So these are the properties of bipartite graph. Okay. Right? Now my question is, can we convert every graph into bipartite graph? Can we convert every graph into bipartite graph? Let me check. Please look at here once again. We converted first graph into bipartite graph. Okay. transforming this graph into bipartite. Similarly, we transform this graph into bipartite graph. So can we convert every graph into bipartite graph? No, it is not possible. Look at this example. Look at this example. Can you convert it into bipartite graph? Is it possible to convert it into bipartite graph? Suppose if I keep one vertex C here, and if I keep it as A and it is B. Now C to A there is an edge, and C to B there is an edge. But the problem is A to B is also there is an edge, right? A to B is also there is an edge. But in bipartite graph definition, no two vertices of the same set can be connected. No two vertices of the same set can be connected. Therefore, we cannot represent bipartite graph for this graph. Okay. Right? Let me check this one. Let me check this one. Can I convert into bipartite graph or not? For example, if I take A and C, A and C at one place, A and C at one place. Remaining we have B and then D, BD and then E. Okay. Now I can say from A to D, A to B, we have edge. So A to B, A to D, we have edge. From C to E, C to B, we have edge. C to D and C to E, we have edge. But what is the problem here? Of course, we have edge from E to D also, right? Means we have to draw edge from E to D, E to D. But in bipartite graph, we cannot allow an edge between two vertices of the same set. You consider this is a vertex set of M. It is a vertex set with the name as N. Okay. We cannot allow two vertices of the same set to be connected. Therefore, it is not a bipartite graph. It is not a bipartite graph. Clear? What did you notice from this? We cannot convert every graph into bipartite graph. We can convert only certain graphs into bipartite graph. Then you may ask question, sir, is there any way to identify which graph we can convert into bipartite and which graph we cannot convert into bipartite? Yes, there is one important property. The property is, suppose if the graph contains a cycle of length odd, then that graph cannot be converted into bipartite graph. Look at here. What is the length of the cycle? Just look at here and tell me what is the length of the cycle. Obviously, length of the cycle is equal to 3. 3 means odd. That is the reason we are unable to convert into bipartite graph. What is the length of the cycle? That is 1, 2, 3, 4, 5. Okay. Therefore, it is also odd cycle length. Therefore, we cannot convert into bipartite graph. It means that a bipartite graph always contain a cycle of length even. Remember that a bipartite graph always contains cycle of length even. Okay. Odd cycle length cannot be converted into bipartite graph. Okay. Let me write that point also. This is the most important point. You have to remember that. Note. Bipartite graph cannot contain a cycle of length odd. Cycle of length odd. Is it clear? Cannot contain cycle of length odd. Remember that point. A bipartite graph cannot contain a cycle of length odd. But if the graph contains even length cycle, or if the graph does not contain cycle, also we can convert into bipartite graph. Okay, but a bipartite graph cannot contain a cycle of length odd. Remember that. Okay. This statement is most important point. A bipartite graph cannot contain a cycle of length odd. Okay. It is useful while doing problems in coloring. Okay. So what we covered in this video, we completed the concept of complete graph, cycle graph, and its properties, wheel graph and its properties, and then bipartite graph, complete bipartite graph. Okay, we have only one definition left out. We'll discuss the definition also. Okay. That is star graph. It is very simple to understand. The star graph is nothing but it is a complete bipartite graph having structure like this: k1 comma n minus 1. Okay, k1 comma n minus 1. Clear? That is a star graph of n vertices. A star graph of n vertices can be defined as k1 comma n minus 1. Means it is a complete bipartite graph. One set contains only one vertex and remaining set contains n minus 1 vertices. For example, I want to take star graph of order 5. Star graph of n is equals to 5. Number of vertices are 5. Star graph of n is equal to 5. In that case, I have to construct k1 comma 4 graph. k1 comma 4 means one set contains one vertex and remaining set contains 4 vertices. Then we can join them. This is called star graph. Okay. And if I ask star graph of order 6, star graph of order 6, that is n is equals to 6. If n is equal to 6, we can represent it as k1 comma 5. The structure of k1 comma 5 is looking like this. That's all. This is known as star graph. Okay. So with this, we successfully completed basic definitions of graphs. Okay. In the next video, we are going to solve workout examples. Okay. You really feel very happy after solving workout examples because you are having complete idea about basics now. Definitely, you will enjoy that workout examples video also. Okay. Thanks for watching this video.